Welcome to chemistry classes by Vijay Kumar Sethi. Class 11th chemistry. We were discussing unit 2 structure of atom, and in this video we will discuss about black body radiation, Planck's quantum theory and photoelectric effect. First come to the black body radiation. Any ideal body which emits and absorbs radiation of all frequencies uniformly is called a black body, and the radiation emitted by such a body is called black body radiation. In practice, no such body exists. Carbon black approximates fairly closely to black body. A good physical approximation to a black body is a cavity with a tiny hole which has no other opening. You can see this diagram. This represents a cavity and this having a small hole or small opening. Any ray entering the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. When an iron rod is heated in a furnace, it first turns to dull red, then progressively becomes more and more red, then becomes white, and then becomes blue as the temperature becomes very high. This means that red radiation is most intense at a particular temperature and the blue radiation is more intense at another temperature. Okay, you can see this diagram. Color temperature. Temperature is represented in the Kelvin scale. This is the temperature. Okay, as the temperature increases, you can see what are the change in color. At the low temperature, this is red, and at the high temperature, it is blue. Frequency of the radiation emitted goes from a lower frequency to a higher frequency as the temperature increases. You can see that is red color has low frequency and higher wavelength, and blue color has higher frequency and low wavelength. Is it clear? The amount of light emitted, that is intensity of radiation from a black body, and its spectral distribution depends only on its temperature. This graph represents the wavelength intensity relationship. Two things we can observe from this graph. At a given temperature, intensity of a radiation emitted increases with the increase of wavelength, reaches a maximum value at a given wavelength, and then starts decreasing with further increase of wavelength. You can see any temperature, in this case two temperatures are shown, T1 and T2. T2 is greater than T1. If we see this temperature T2, okay, if you observe this graph, as the this side wavelength and this side, this is intensity. As the wavelength increases, intensity first increases, reaches at the maximum. Then as the wavelength increases, this intensity decreases. Okay. Also, as the temperature increases, maxima of the curve shift to short wavelength, that is higher frequency. Now, if we compare these two lines, that is temperature T1 and temperature T2, and this is the maxima. At the lower temperature, this maxima is at higher wavelength. Okay, and at the higher temperature, this maxima is at lower wavelength. Lower wavelength means higher frequency. These results could not be explained on the basis of wave theory of light. Okay. Then another theory regarding light, Planck's quantum theory, came into existence. It was given by the Planck. Atoms and molecules emit or absorb energy only in discrete quantities. Okay, that is, this discrete quantity is called packets, and not in a continuous manner. The smallest quantity, that is packet, smallest packet of energy that can be emitted or absorbed in the form of electromagnetic radiation is called quantum. Okay, and plural is quanta. Okay, for one packet we use the word quantum, and for more than one packet we can use the word quanta. Again, you have to remember, a quantum of light is called a photon. Clear? Now, what is the difference between quantum and photon? Quantum is the smallest packet of energy, and this energy may be from any source. But if this energy is a light, then this small packet of energy is known as photon. Okay? The energy of a quantum, or we can say energy of a photon of radiation, is proportional to its frequency. That is, E is directly proportional to nu. And this, if we remove this proportionality constant, then another constant will come, that is H. And this H is known as Planck's constant, and it has the value of 6.626 into 10 raised to the power minus 34 joule second, and this equation is known as Planck's equation. A body can emit or absorb energy only in terms of integral multiple of h nu. That is, E is equal to n h nu, and this n, okay, it will be n. N is equal to 0, 1, 2, 3 and so on. It means this energy is quantized. Okay, now what is the meaning of this quantization of energy? The restriction of any property to discrete values is called quantization. Quantization can be compared to standing on staircase. You can see these two diagrams are shown. This represents the continuous nature of energy, and this represents the quantization of energy. A person can stand on any step of a staircase, but it is not possible for him or her to stand in between the two steps. Again, I think you can understand easily that each person can stand to this place, or these two places. That is step. But it is not possible for a person to stand at this place. Okay. In the same way, the energy can take any one of the values from the following set, but cannot take on any values between them. That is, energy may be equal to 0 or h nu or 2h nu or 3h nu and so on. It may be n h nu. It may not be there between these two. That is, 2.5 h nu energy is not possible. In the same way, between these two, 1.5 h nu energy is not possible. With quantum theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or wavelength at different temperatures. Means as temperature increases, frequency will also increase. That's why there is a change in color in the radiation from a black body or radiation from a hot body. Photoelectric effect. It studies in 1887 by H. Hertz. And what is this? Ejection of electrons from certain metals, for example potassium, rubidium, cesium. When light of suitable frequency falls on it, is called photoelectric effect. This is the one equipment for studying the photoelectric effect. In this case, this is a metal surface, metal plate. This is the light falls on this metal plate. Electrons are ejected, and this is a detector which can count these electrons and also can measure the kinetic energy of these electrons. Light of a particular frequency strikes a clean metal surface inside a vacuum chamber. Electrons are ejected from the metal and are counted by a detector that measures their kinetic energy. Observations of photoelectric experiment. The electrons are ejected from the metal surface as soon as the beam of light strikes the surface. That is, there is no time lag between the striking of light beam and the ejection of electrons from the metal surface. Second, number of electrons ejected is proportional to the intensity or brightness of light. We can say this intensity is represented by the amplitude. We can say number of electrons ejected is proportional to the amplitude of the light. For each metal, there is a characteristic minimum frequency, and that is known as nu naught or nu zero, also known as threshold frequency, below which photoelectric effect is not observed. At a frequency nu greater than nu zero, the ejected electrons come out with certain kinetic energy. It means the frequency of striking beam of light is greater than threshold frequency, then this extra energy impart kinetic energy to the electron. The kinetic energies of these electrons increase with the increase of frequency of the light used. All the above results could not be explained on the basis of laws of classical physics, that is wave theory. According to classical physics, the energy of the beam of light depends upon the brightness or intensity of the light. In other words, number of electrons ejected and kinetic energy associated with them should depend on the brightness of light. But practically, it is verified that number of electrons ejected does depend upon the brightness of light, but the kinetic energy of the ejected electron does not depend on the brightness. Kinetic energy of the ejected electrons depends on frequency of incident light. For example, red light with the frequency of 4.3 to 4.6 into 10 to the power 14 Hz of any brightness or intensity may shine on a piece of potassium metal for hours, but no photoelectrons are ejected. But as soon as even a very weak yellow light having frequency 5.1 to 5.2 into 10 to the power 14 Hz shines on the potassium metal, the photoelectric effect is observed. The threshold frequency for potassium metal is 5.0 into 10 to the power 14 Hz. It means minimum frequency is required to eject the electron, and this minimum frequency may be different for metal to metal. And these observations can be expressed in these plots. It is plots based on observation of photoelectric effect. This is between frequency and kinetic energy of ejected electrode. This is the minimum frequency, and the frequency greater than this is used to increase the kinetic energy of ejected electron. Okay, this is frequency of light and number of photoelectrons. Number of photoelectrons are not affected by the frequency of light. Photoelectrons means ejected electrons are known as photoelectrons. This graph is between intensity of light and number of photoelectrons. Okay, and this is directly proportional, but condition is there, that is this nu should be greater than threshold frequency. After threshold frequency and intensity of light increases, then number of photoelectrons will also increase. But this intensity of light will not affect the kinetic energy of ejected electrons. Condition is again there, that is frequency of incident light is greater than threshold frequency. Clear? These graphs are important. Explanation of photoelectric effect. Einstein explained the photoelectric effect using Planck's quantum theory of electromagnetic radiation. He received the Nobel Prize in Physics in 1921 for his explanation of the photoelectric effect. When a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. Greater the energy possessed by the photon, greater will be transfer of energy to the electron, and greater the kinetic energy of the ejected electron. In other words, kinetic energy of the ejected electron is proportional to the frequency of the electromagnetic radiation. We can explain with the help of these formulas and equations. Energy of striking photon is h nu. The minimum energy required to eject the electron, that is this h nu 0. This is also called work function, represented by this is W naught or W0. If h nu is greater than h nu 0, that is energy of the striking photon is greater than the work function, then the kinetic energy of the photoelectron is given half mv square is equal to h nu minus h nu 0 is equal to this h is common. Okay, then we will get this expression. And actually this expression is according to conservation of energy principle. H nu is equal to h nu 0 plus half mv square, where this m is the mass of electron and this v is the velocity of ejected electron. A more intense beam of light consists of larger number of photons. Means if intensity is more, number of photons will be more. Consequently, the number of electrons ejected is also larger as compared to a beam of weaker intensity of light. Is that clear? Thank you.